Good afternoon, everyone, and welcome to our NITheCS webinar. And to give a brief overview of the webinar, I will hand over to Prof Surab.
Good afternoon, everyone. Thank you very much, Tetokile. So this is a special webinar because we're going to have more of them in the near future. A series of webinars that comes out directly from the Mathematical Structures and Modeling Research Program at NITheCS. You can find out about this program, those of you who are not aware of it, you can find out about it on the website of NITheCS. The understanding is that the members of this research program are as actively involved in the webinar as possible. And the webinar will be a platform for us to exchange our ideas and form new ideas and also collaborate and so on. And so in this first one from that series, the talk will be given by Professor Watson. Tetokile will still introduce him more properly than I do currently. He's one of the PIs this year for the research program. We also are happy to have other PIs who want to join us for this year. The responsibility of a PI is to collaborate with as many members of the research program as possible. So it's quite a heavy duty responsibility. But then also there is a lot of, I mean, the research program is quite active program, so there is a lot going on there. And we want to make sure that we make progress, significant progress every year. So over to you, Tetokile, to introduce the speaker.
Thank you so much, Prof Surab. So everyone, as Prof Surab has mentioned, today we have Prof Watson, who has a PhD in multiparameter inverse spectral problems. And he obtained the PhD from WITS. And he has served as a postdoc fellow at the University of Calgary. And currently his research areas focus on spectral theory of differential operators, inverse spectral theory, stochastic processes, which you'll be talking about today. And he has been the head of the School of Mathematics at WITS for 7 years, and currently he's the interim director of the Center of Excellence MaSS. So, Prof Watson, we are really grateful to have you here to give this talk, and one of many. And I hope it's quite engaging to the audience. And also, just a note to the audience for the POPI Act, the recording of this talk will be uploaded to YouTube. And also this, for Prof Watson, it will reach even more people on our YouTube channel. So over to you, Prof.
Great, thank you. I think we at last have got to the point where you can see the talk and hopefully you can hear me.
Yes, that is correct. Can you put it in presentation mode, or maybe it will give us issues again?
Let's just try.
Bruce, can I ask you a question before you begin?
Yes.
Do you want us to listen to you without any interruptions, or do you not mind if every now and then we ask you something during your talk?
I'm perfectly happy with interruptions. It doesn't particularly worry me. I'm just trying to get this to full screen mode. That's my. Is that better? Is that better?
Yes, that's better. Just one last thing quickly, sorry. Which of your two devices will you be using?
Sorry?
Because I think there is an interference.
Yes, I'm just going to. Yes, I have two different sessions running.
Yes, so there is an interference. Okay,
Okay,
perfect.
it should be a clean version now. Has the interference stopped?
Yes, yes.
And
Perfect.
I actually
Looks good.
I'm fortunate today to have with me here another member of our research team, Anka Kaluch from the University of Dresden, TU Dresden, in person at this end. Okay, this is a research project that started in the early 2000s with Kunrad Labuskachny, now deceased, and Wenqi Kuo, still an active member of the project. And this was modeling stochastic processes in vector lattices. And the starting point of studying stochastic processes begins with the easiest of these objects, which is your expectation operator. You start with a probability space, which is a special case of a measure space, one in which the measure of the underlying set of the whole space is 1. So that's as shown here, you have an underlying set, a sigma algebra of subsets, and a measure. And the measure of your underlying set is 1. We take as our random variables the integrable functions, the L1 functions over that set. And your expectation operator, as is well known from statistics, is the integral over your space of your random variable. Now, if one wants to look at this in a more functional analytic way, you can also consider this as a map back into your underlying L1 space, where it gives you the AE constant function with the value of your integral. And this leads us into the next concept, that of conditional expectations. For a conditional expectation, we have our underlying probability space, we have the L1 space over it, and we now take a subsigma algebra of our original sigma algebra. So let's take sigma as being a subsigma algebra of our original sigma algebra F. And we want, whenever we average over a set from the subsigma algebra, it must be the same as averaging over the set. So when we take the conditional expectation operator, it has to be measurable with respect to the subsigma algebra. And when we average over any set from that subsigma algebra, it must be the same as averaging our original function over that set. So in short, this gives you that the integral of your conditioned object, that's capital F, a set A from your subsigma algebra must be the same as the integral of F over the set A, the original random variable F over the set A, as shown in Formula 1. And the capital F here is denoted by the E of F given sigma. And if you have a discrete space as your underlying set omega, one can these conditional objects, but beyond that, you need to use the Radon-Nikodym theorem to show the existence of conditional expectation operators. And here we observe that your conditional expectation operator, there's a typo there, please excuse that. That should be conditioned on sigma. If you look there, sorry about that, there's a typo over there. There's a typo there, that should be a sigma, sorry. And your conditional expectation with respect to sigma takes you from the L1 space over omega F mu and takes you into the L1 space omega sigma mu, which is a subspace of L1 omega f mu. And this map is a positive order continuous projection onto L1 omega sigma mu. Now, in a relatively old paper by Riesz, and this is based on earlier results by Douglas and Ando, he gave a characterization of conditional expectation operators via contractive projections. He was working on a probability space, and he was looking at the LP spaces, one for P between 1 and less than infinity. And he took T as a map from LP to LP. It's a positive contractive projection that maps the identically 1 function to the identically 1 function. Then that is equivalent to T being a conditional expectation operator with respect to some sigma algebra of our original space. This result of Riesz and Sadak was based on the earlier work of Douglas and Ando. Douglas characterized positive contractive projections, range spaces of contractive projections, as well as conditional expectation operators on L1 spaces, and Ando extended these results to LP. But we will return to Douglas's result later in the talk. This led us to define a conditional expectation operator on an Archimedean Riesz space with weak order unit as follows. We defined it to be an operator, which is a positive order continuous projection on the space with range, a Dedekind complete Riesz subspace of the original space. And it has to have the property that it maps a weak order unit to weak order units. This
Sorry, Bruce, if I can interrupt.
Yes.
Sorry, Bruce, if I can interrupt and ask you, what is a Riesz space?
Okay, more commonly known as a vector lattice. They are one and the same. So it is a vector space, and it has lattice operations on it. It is partially ordered. Okay.
But by lattice, you mean lattice in the sense of order theory?
That's right. It's partially ordered. And the partial order is compatible. If you have the partial order, you can build a lattice structure. In other words, suprema and infima, and vice versa.
Is it a complete lattice?
That is, if it's Dedekind complete, it becomes a complete lattice.
Right.
And there also needs to be a compatibility condition between your algebraic operations and your lattice operations. And these are the well-known ones that if you have a positive object, so if we think in terms of partial orders, if you have an object in your space that is above 0, and you multiply that by a real number that is positive, resulting object in your vector space is above 0. And similarly, if you have an object that is above 0, well, if you have two objects, x and y, and x is comparable with y, with x greater than or equal to above y, and you add to both sides of this some vector z, you retain that partial ordering. So those are your compatibility conditions with your algebraic operations. And this makes it into what is known as a vector lattice.
And what is a key example of that? The motivating example?
Well, we can start off with Rn. We can go to all of the LP spaces, real LP spaces. You can do CX.
So what is the partial order on Rn? What is the order on Rn?
That is component-wise ordering. So if you have a vector x less than y, it means that xi component xi is less than or equal to component yi for all I.
Great, thank you.
You can do it on the little LP spaces as well. And there are quite a few more obscure examples. So, but those are very well-known examples.
Thank you very much.
If you take the space of all maps from some underlying set to the reals, that again is a vector lattice. Not a very nice one if your space, if your underlying set X is large, but it is still a vector lattice. And
great.
By Archimedean, we mean that if we have a downwards directed net in the space, a generalized sequence, in other words, that's downwards directed, then with infimum 0, if I well, okay, a nicer way to characterize that is if I have a non-negative object in my space, let's call it V, vector, and so it's greater than or equal to 0 in the space, and I take another element of the space that I can sandwich between 0 and 1 over n times V for all n, that other vector must be 0. So it means that I can sandwich anything between 0 and something infinitesimally small. There's nothing, there's no gap if you do all the limiting operations. And this guarantees uniqueness of limits.
Great. Thank you very much for the elaborate answer.
So, and your space of measurable functions without even real valued measurable functions, if you take almost everywhere equivalence classes of those, that again forms or Riesz space. Again, and it has a weak order unit, which is an object which I will, maybe I should unpack what a weak order unit is as well.
That'll be helpful.
If the listeners remember in a standard measure theory course, when you do the Lebesgue integral, one of the fundamental results is that you can approximate any measurable, non-negative measurable function. We can approximate it from below by cut-off versions of it. And this is one of the basic tools in how you approximate measurable functions. And that very property is what characterizes weak order units. In that case there, it is the one function that you've used. You've sliced up your function by multiples of your one function. And if for a space to have a weak order unit means that if we take any non-negative element in our vector lattice, we can take the, let's call our candidate for weak order unit E, little e, that has to be non-negative. And if we take our arbitrary non-negative element of our Riesz space and we take the infimum of our element F, our non-negative element from the Riesz space, with n times E, and we take the supremum of that infimum. So in other words, our infimum of F and NE chops off F at the height NE. And if we take the supremum of all those chopping offs, we have to get back F. So that means when you can always approximate objects in your space by truncated versions, which are bounded by a multiple of E as your approximates in order limit. So that tells us a little bit about the structure there. Some examples are, so the reason, one of the motivating reasons behind this is if you take your L1 space with AE equivalence classes, that is a vector lattice, and it has if we take a finite measure or probability measure, basically one function is a weak order unit. It enables us to chop off the elements and use those truncated versions as approximants. So L1 is a Riesz space with weak order unit. And as we noted before, well, back to a classical conditional expectation. Where are we here? If we go back here and we look at what happens to non-negative objects. So if we take a little f that is greater than or equal to 0, and we condition it on a sub-sigma algebra, we end up again with a non-negative object. So expectation map on L1 takes non-functions to non-negative functions. It is a projection, it's idempotent. So it's positive, it's idempotent. Order continuity, the easiest way to look at order continuity is if I have a net, which is a generalized sequence of non-negative objects, vectors, which is descending, or downwards directed, and has infimum 0, then I can take that limit. So if I take T of that net, so now I had a net of objects F alpha, and I take T of F alphas, because T is positive, that will again be a downwards directed net of non-negative objects, and the infimum of that new net must be 0. And that characterizes the order continuity of T in this case. So very classical operator theory, over Banach spaces and Hilbert spaces, we work with order continuity at 0. Once we have that working, we are in business. So that is our definition there. And a typical example of this is your conditional expectation operator on Rn. Sorry, on L1. You can do this on Rn as well. And then what you find is that your conditional expectation operator averages over particular coordinates of your vectors. So you can then, you can write it as a matrix which averages particular components of your vectors. And it has to be an idempotent positive matrix that retains the weak order unit. It has to be stochastic. And the next concept we should look at is that of strict positivity, where that means that the only non-negative object, only non-negative vector that is mapped to 0 is the 0 vector. That does not mean that your conditional expectation operator T here is 1-to-1. And one can see this immediately from just your integral on the unit interval, for instance, Lebesgue integral with respect to Lebesgue measure over the functions on the unit interval. That gives you an expectation operator, and hence a conditional expectation operator as a special case. You can have functions which are negative on some part of it, positive on another part, but their integral is 0. But that does not mean that the map is not a positive map. If we take a non-negative function and integrate it over the unit interval, for that, with respect to Lebesgue measure, that integral will be 0 if and only if the function f is almost everywhere 0. So the non-negativity there is critical. So that leads us back to what our conditional expectation operators look like in Rn. in L1. And if it is not strictly positive, one can always build a quotient space. So that is not critical. And some examples. We've talked about quite a few of these already. L1, classical L1, over a probability space omega f mu, and sigma, a sub-sigma algebra of f. Then this is Dedekind complete. I'll come back to that matter in a moment. And so that comes back to Zurab's question about it being a complete lattice. If it is Dedekind complete, it is, well, but I'll talk about that. It has as a weak order unit the identically one, or the almost everywhere one function. That is by far not the only weak order unit. In fact, every L1 function that is positive almost everywhere is a weak order unit for L1. So there are many weak order units. One must not imagine that if a space has one weak order unit, then there is only one. There are many. And here your well-known measure theoretic or probabilistic conditional expectation is a conditional expectation operator in the Riesz space sense. So that if this example were not to work, we would be in trouble. But there are more complicated examples, which hopefully we will get to. Yes, Dedekind completeness. This is if we have a set which is bounded above in our vector lattice, then it must have a supremum in the vector lattice. So any set which is bounded above has a supremum. Any non-empty set which is bounded above has a supremum. So that is what Dedekind completeness gives. And so while we showed that our measure theory probabilistic conditional expectation operator was a Riesz space conditional expectation operator, we have a degree of consistency here. If we take as our underlying Riesz space L1 over a probability space, and we have on this Riesz space a Riesz space conditional expectation operator, then we are guaranteed that that is a probabilistic conditional expectation operator, and that follows from the results of Riesz, Douglas, and Ando, principally Douglas's case, because Douglas was specifically concerned with the case of L1 omega f mu. Oh, it's not good. It's not. The version of Riesz space conditional expectation operator that we decided to work with at the beginning, in about 2001 or 2002, is not the only generalization that has been considered. De Maar in 1966 looked at generalizations of martingales over vector lattices, and he used positive order continuous projections. He did not make a condition that they had to map weak order unit to weak order unit. Now, the concern here is that this contains within it a class of operator which is most distinctly not a conditional expectation operator when you apply it to L1. If one considers on L1 the map given by multiplying a function by a characteristic function of a set, of a measurable set. So if we take we define that map, let's call it P subscript A, where A is a subset of omega, and we form the map that maps F to F times the characteristic function of the set A. That meets all of DeMar's conditions, but it fails most distinctly to be a conditional expectation of probabilistic sense when we apply it to L1. So that definition of a conditional expectation operator falls short of what is needed. And it doesn't say anything about the Dedekind completeness of the range space. And that is quite a critical assumption, especially when you're working in infinite dimensional spaces, like L1. If you're working on Rn as your vector lattice of random variables, then because it is finite dimensional, a whole lot of things come out for free. But as soon as you're working on L1 over omega F mu, where omega has infinitely many points and your measure is, let's say, it has some complexity, you fall short of what would be needed in the probabilistic sense. George Stoica, sorry, I can't see my bottom of my slide here because my system has decided it wants to block it. I can't give you the date, but again, it was, I think, in the 1980s, around 1983, if my memory serves me right. He looked at conditional expectation operators on vector lattices and on Banach lattices. And he put in so he took them as positive order continuous projections, P, with a boundedness type condition for all F, positive in the space, from all F non-negative. Now, this again, it's a nice generalization. It's better than DeMar's one. It's closer to what you want. But again, it still falls short of giving you back everything that you would hope from a probabilistic setting when you put it back there. A third extension, which happened fairly recently, was instead of Dedekind completeness and order continuity, the authors used sigma Dedekind complete and sigma order continuity. In other words, instead of working with nets in the vector lattice, they worked with sequences. Now, this is an interesting generalization. So I'll talk a little bit more about it. So DeMar's version is the most general, but it falls short. The Dedekind complete version makes some more assumptions than Stoica's. Well, Stoica's version is a little bit less restrictive, but still doesn't get us back to what we would want when we work on L1. Both the Dedekind complete version of the definitions and order continuity and the sigma Dedekind complete and sigma order continuous versions give exactly the same generalization in the case when you take it back to L1 omega F mu, where mu is a probability measure. So they are equally good there. The sigma Dedekind complete and sigma order continuous is more general, but again, you don't get, well, you assume less, you get less. So what we worked with is the Dedekind complete version, in that it leads to both a good theory, a rich theory, and a strict generalization of the L1 version. But when restricted back to L1 gives you what you would hope for. And this condition here that the range is order closed or Dedekind complete in its own right as a subspace is rather important when you start working with conditional expectation operators generated by stochastic processes. That comes in as a critical constraint. Sorry, I just need to get a glass of water. If you can stay there.
Meanwhile, I'd like to encourage participants to write any questions if you have any in the chat, or if you want to ask them, you can also do so.
Okay. There we go. Now I can see the bottom of my screen as well. Now, this is distinctly not sequential in the order in which we developed the theory over the years. We've been working on these results now we've been working in this area and these results for about 25 years now. That's Wenshi Kunad-Labuschagne before he died, myself. Koos Krobler also was involved, doing some continuous time work, etc. So over time, we have built useful pieces of machinery that when you look back, you would have liked them early on in the theory. So what is being presented here is not chronologically as it was developed, but what we found as critical results later on as we went through it and said, well, we could have built a better theory if we had known this earlier. And this slide here is one case in point. And the concept of T-universal extension of a conditional expectation operator. When one starts off with a space of functions and you build L1 out of it, you extend the space and you extend your operator to the Lebesgue integrable function. So you could have started off with the, let's say, step functions, something like that, or you could have started off with the continuous functions. And then you have applied a completion operation to it using limits and nets to the maximal domain on which you can still have a conditional expectation operator, or in the case of Lebesgue integral, on which you can still have the integral well defined. So this is the same procedure that is used here. And we start out with an Archimedean, well, in our case, when we published it, we actually did it for the case of a Dedekind complete respace. But in actual fact, you don't need that. You can start out with an Archimedean respace. And, well, let's talk about the Dedekind complete version, because we start out with our respace and a conditional expectation operator on it. We would like to build the maximal domain of that to which you can extend that operator and retain it as a conditional expectation operator. And to do this, one needs one more concept, and that is the universal completion of a respace. Now, if you have a respace, a vector lattice, and you look at disjoint objects in that space, in other words, let's take non-negative objects, non-negatives in the space, if they're disjoint, if their infimum is 0, then they're classed as being disjoint. Now, you would like to have the property that if you have any family, not necessarily sequence or anything like that, a family of disjoint elements from your space. So every vector in your collection is disjoint from every other one. You would like to be able to take the supremum of that family and end up in your space. And it so happens that you have there is a well-defined way to extend your original Riesz space so that happens. And that is called the universal completion of your Riesz space. So it is tacking onto your space and building into your space all the elements that are formed via taking disjoint suprema and then building your space from there. And the process for this can be found in Zarnin, in various papers of Zarnin, and it has been well studied in the framework of vector spaces. Okay, so that is your biggest sensible extension of your original space. But that is like taking your measurable, your functions over a given set that let's say it's a function space, and now we build every disjoint. If two functions are non-negative and they have infimum 0, then we allow their summation to primum, that'll be the same, to be in the space. If they're pairwise, if it's an infinite family, we can only talk about the supremum. And we build that symbolically, and that gives us a new Riesz space, a very big Riesz space. And most of your classical function spaces live inside, have as their universal completion L0, your measurable functions. So that is a universally complete Riesz space. And if you take L1, your integrable functions, its universal completion is the measurable functions, the space of measurables, which is, as we know, far larger than just the integrable functions. Now, to extend our conditional expectation operator, we look at all non-negative objects in that universal completion that can be approximated, that can be characterized or represented as the supremum of an upwards directed net of non-negative objects from our original space. There, from our original space. So we take this net, it's upwards directed, it's from our original space, and its supremum in the universal completion is the object. And if we look at all such objects, those form our non-negative objects that are, yes, and we want, sorry, that's too big. And we want that when we apply T to this net, it has to also be bounded in our universal completion. So our object F, universal completion, non-negative object F from our universal completion has to be the supremum of an upwards directed net from the positive part of our original space. And when we take our conditional expectation applied to that net, that it has to be bounded in our universal completion. In that case there, we put that F into the domain of our extension, and we take the value of, or the conditional expectation of that F as being the supremum of T applied to that net F. Now, so that gives us all the positive objects or non-negative objects of our space E hat, which of the T universal completion or maximal domain of our conditional expectation operator. And then we form the differences of positive objects, of non-negative objects, and that gives us back our entire space. Now, some things that can be shown, this space E hat, what's happened to my screen? Okay, sorry. The space E hat, let's just go back there, is a Dedekind complete respace. It has our original weak order unit as a weak order unit. It contains our entire original respace. It is a respace in itself, in its own right, and it is T universe. And with respect to our extended operator, here we have how we form the extended operator. So we've built the space. I told you how to build the extension of the operator by taking the supremum of T applied to the nets, the net that approximated F. So that gives us the extension of the operator, and that builds the operator on the positive cone. And so we apply the operator to each of the positive parts. And so the positive part of, we built our space E hat as differences of positive objects. And now we can apply T hat to those positive objects. And so if we have F is a difference of two objects, F plus and F minus, we apply T hat to each of those and form their difference. If this is done with due care, you end up now with a well-defined, the first thing is that it's well-defined, your T hat is well-defined. It is a map from E hat to E hat. It is a conditional expectation operator, it's order continuous, it is a projection, it has, and the range of T hat is Dedekind complete, and it is actually one thing more, which because I'm running out of time here and I'm going quite slowly, it has one extra property that we only discovered many, many years later, that when we take the range of T hat, that is again universally complete in its own right as a respace, which then means it's actually an algebra, so that the range of T hat is a very special object. It's a ring. It's not just a vector space. We can multiply objects and it has extremely special properties, but that is, I think, talk. Now, I'm not sure whether my audience would like me to stop at this point. We can continue. This is really square one of the building of stochastic processes in vector lattices.
Bruce, I think it might be a good idea to continue next week if you're still available to do that.
Okay, that's fine, with pleasure.
And perhaps one could also maybe consider giving there are these monthly schools for introducing basic concepts. Maybe one could give a monthly school on something that lasts for 1 month on Riesz spaces. Okay. And if I'm not mistaken, April might be available month for that. If that's yeah.
And then I can unpack things in careful detail then. so that all
Sure,
these,
yeah, like the more basic
different aspects are explained with due care and detail that people can follow it step by step.
Yes, so that monthly school is intended more for postgraduate students than researchers, but I mean, probably the idea would be for our research program to learn about these things in more detail.
Yes, with pleasure. I'm at the moment composing a 100+ page survey on this area for Berkhauser.
Fantastic.
So this will fit in and make me work harder on it and faster.
We could perhaps still allow some questions before we end off today's session. Are any questions from the audience?
I wrote it in the chat. What is the universality of this construction?
Sorry,
What is the universality?
The question is what is the universality of the construction? In what sense it is universal, the construction?
Okay, that is okay. It does have a commutative diagram that it can be built by.
No. Do you mean to say that it is the largest? It is the largest Riesz space with a conditional expectation operator or any such thing?
Well, the first point is to start with your universal completion of your Riesz space.
Mm-hmm.
Okay, so that has a commutative diagram by which it can be shown, by which its universality is defined. The universality, well, our conditional expectation operator, the domain of that is maximal domain to which you can extend your conditional expectation operator as a conditional expectation operator. So yes, it is the maximal extension of it.
So in some sense resembling the analytic continuation of a function, right? Almost the largest.
To some extent, yes.
Yeah.
If you want to take it into an entirely different domain of mathematics, yes.
Yeah, so it's the largest place to which I can extend this conditional operator.
Yeah, and it stays of the same type. You want it to be a conditional notation, yes. So yeah, that is exactly what it is. It is the maximal you can maximal extension of it, and still have the essential properties that we want.
Yeah, it's very nice and interesting. Would be nice to listen to you again.
Great.
In more
detail. Part 2 next week. Same time, same place. And hopefully I won't have as many
questions from anyone else? Maybe time is running out. Can I also ask a very quick question, Bruce?
Yes.
You said that this is constructed by this completion is constructed by taking disjoint sets and then not sets, sorry, disjoint elements, and then
disjoint elements and taking the suprema.
Yeah. Now, what kind of sets in the space have joints? So those that are disjoint, probably not always, because otherwise you wouldn't be taking the completion. What about those who have a lower bound? Do they always have a join?
Okay, so when you build the universal completion, you are only looking at non-negative elements in your space. You're building the positive part of your space.
Yes, now
so you have
I'm asking about the positive elements of the original starting space. If I take positive elements and I have a set of positive elements which is bounded below by a positive element.
Well, it's bounded below by 0, yes, because they're positive.
No, but bounded below by but 0 doesn't count. Let's exclude 0, because when you define,
Okay.
because your sets that you're taking join off, you allow them to have. You're saying that 0 is the only lower bound, right, for those sets?
Well, we're working with so if you think of functions, we're looking at functions which are non-negative, and if you look at the support of the function, where a function is non-zero, you're allowed to look at another function which is non-zero on a different set, and you can take the supremum of those, and you can take the supremum of any such family, so long as when you compare any two, their infimum is 0. So in other words, their supports are disjoint.
That you do for constructing the completion, right? But
That's
my
for
question,
constructing universal completion, yes.
yeah, but my question is, which of the supremums exist already in the starting space?
Pairwise suprema exist. So, and if your original space was Dedekind complete, if you had any bounded set of objects in the space, you could take those supremum, the supremum of those. So if your set had a universal bound, you were allowed to take a uniform bound. You could take the supremum of your set. That's guaranteed by Dedekind completeness.
But it needs to have an upper bound, not just lower bound, right?
Yeah.
Okay.
But you could take, for instance, if you just think of, let's take L1 over the reals, or L infinity over the reals even. It's a worse example. And it's a Riesz space, it's Dedekind complete. Every function in L infinity is AE bounded. So you could let's take step functions on the interval 0, 1 that has value 1, on the interval 1, 2 that has value 2, etc., going on. And let's make them 0 on the integers where they intersect. Okay, that's an unbounded family. Each element there lives in L infinity. You cannot take the supremum of that family of functions in L infinity, but you can take the supremum. The supremum of that certainly lives in the universal completion of L infinity as your measurable functions.
Thanks. I'm asking this because this construction is similar to something I'm working on a completely different topic. I wanted to know how similar they are, so that's why I asked the question. But I'll tell you more separately.
Okay.
Thank you very much for the answer. Any other questions? If not, then I'll hand over back to Kila to close off the webinar.
Thank you, everyone, to the attendees for attending, and to Prof Watson for taking time to give this lecture. And thank you, Prof Surab, for suggesting that this becomes a mini school. So I've made a note, and I will raise that thought on Monday. So again, thank you so much. And I hope this recording will get more viewers, and we will get even more people for the mini school. And it seems like there's a lot of interest, and an hour was not enough. So thank you so much. Those that haven't signed up for our mailing list, please do so. And again,